שזה אתמול יום אחד, שזה ראתה אותה, בדקתי בניוז פורום, וזה לא שלח לנו, לא ידענו, וכאילו, חלק אני מניחה עדיין עובדים, ויש לנו מבחן גם ביום ראשון. וכאילו אין שום, כן. אז אין כאילו שום סיכוי, גם מי שראה, אבל אני חושבת שהרוב לא ראו, יום אמרה לי שראתה במקרה לפני יומיים, ראיתי אתמול, חלק לא ראיתי.
היא ראתה שיש תרגילים, נכון?
לא, היא ראתה שאת עושה את התרגיל, אבל במקרה...
היא לא ראתה שהייתה הודעה בפורום.
לא, אני נכנסתי לפורום, אין הודעה. וגם אם פרסמת, אף אחד לא קיבל הודעה. וגם לא ידענו אם זה התרגיל האחרון או שכאילו...
עוד עניין אחד, יש לנו מבחן כבר ביום ראשון, אז אם אפשר לתת קצת יותר...
אוקיי.
מבחן ביום ראשון בכל שאר המשפט. וגם, מותר לנו לא להביא תרגיל אחד? כן? ויהיה עוד תרגיל חוץ מזה?
כן, עוד תרגיל.
ומתי? מה שאני מצאתי להיות, ממש חלק לקחתי ממנו, אבל אני יכולה להגיד, אני לא יודעת איתך.
אני פרסם אותו משבוע.
ועד מתי?
כאילו אני לא יכולה להגיד אותך, אני לא חושבת שזה נמצא בקש.
עוד שאלה, מתי נקבל את הציונים של התרגילים הקודמים, שנדע אם אנחנו יכולים באמת לבטל?
כאילו אני ציונתי מניח שוב, הוא צילם ממני, אבל זה גם די גרוע, זה לא כן, אבל אם לא, אז אני אעשה את כל המצלמות, סבבה? רגע, מה סוכם? מה סוכם?
לא סוכם.
את צודקת, אין הודעה.
אני גם בדקתי לפני כמה ימים, אז לא יודע.
עד הסוף של
הוא לא אמר לי שלא נראה לי.
החומר של התרגיל האחרון עמד בפולוקו או שנלמד היום חלק מזה? אמרת שלא סיימת.
אני חושב שאפשר להציג את התרגיל כמו שלמדנו בשיעור שעבר, אבל היום סטטיסטית.
כן, זה ממש
אני פרסמתי שהיה ביום ראשון, אבל מסתבר שההודעה לא עלתה לפורום.
איזה זה?
לפי הערכה, כן. אז יום... תרגיל קצר, כן.
אוקיי. עשינו כבר מבחן יום ראשון. עשינו כל שבוע מבחן.
פרסמתי תרגיל חדש. אני חשבתי שכתבתי הודעה בפורום ומסתבר שהיא לא התפרסמה. זה היה אמור להיות ליום ראשון הקרוב, אבל כנראה לא יעבוד. לא, אנחנו ניתן לכם עוד 3 דקות נגיד.
זה נדחה?
מה?
זה נדחה?
למה שאלתם?
זה יידחה, כן.
מתי? יש את הרצון למבחן?
כן, יש את הרצון למבחן. 17 אם אני לא טועה.
חודש, וואו.
הם אמרו לי שלא הייתה להם הפסקה. כאילו, זה אנחנו מסתכלים קצת. let's start with a few announcements. So some of you noticed that there is a new exercise on the web, exercise 6, and that exercise 3 was returned to the box. I thought I wrote a post in the forum about this, but apparently it wasn't posted, so I'm sorry about that. And I will postpone the deadline for exercise 6. If you have restrictions about this, then please tell me. So I would like to know what your exam schedule is. Okay, and we will also have a new in exercise 7 dealing with what we learned last week and what we will learn this week. It will also be a short exercise like exercise 6, and as you know, you can pass on submitting one exercise. You may submit 6 out of 7 exercises. In any case, your grade will be composed of the 6 best exercises. Okay?
Maybe you can the due date should be the date of the exam, and then we do it when we study for the exam. We can have neural networks before and similarity before dynamics. I mean, for me, it's hard to do exercise in dynamics when I know that I have
Okay.
exam in neural networks and we don't have model bet. And I mean, it's hard to find few days
Yeah.
during the application to study to do the exercise.
Yeah. Okay. So yeah, that's an option. So if I postpone the due date, then it can be, not by a week, but it can be by a few weeks. It's not too bad.
Make it short as possible, the exercise, because you don't have
What?
Make the exercise as short as possible.
The exercise is very short. 2 people already submitted it, and exercise 7 will be quite short. Okay. Okay, and so we have the exam on the 17th, July 17th, and we'll have a review lesson before that. So I think it would be good to have it. I think July 17th is a Thursday, so we can have it on Sunday or Monday before that. Okay? Or if you want, we can have it even earlier.
Every Thursday we have.
Okay. Okay, so we can have the review lesson. Okay, on Sunday or Monday, we can have a vote on the internet. Or we're missing Carmel, and it's hard for me to remember who we were missing.
She's stuck in traffic, so.
Okay. Okay, so there are not enough people here to vote. So we'll have a vote or something, and either a Sunday or a Monday, I guess. Sunday might be too early for a review lesson. Okay, so to pick up from where we stopped last time, we were trying to find the average number of events in a point process. And this was average n in brackets. And by summing over this indicator that we made up to help us, we arrived at this expression that we don't know how to solve because we don't have the Q function. Yeah?
Can you say what these indicators are exactly?
Wait a minute. I'll write this down, and then you'll need to say that again because they didn't hear you. Yeah, say again?
What's the intent
Of the indicator? Um, so the indicator is a kind of switch that gets a value of 1 if there was, if the event tau sigma was inside the range TA to TB. Okay, and if that event was outside the range, then the indicator is 0. Okay. Okay, so this is a multidimensional integral over the QS function that we don't know it explicitly. We'll make some assumptions later. Yeah.
you want counting for all the time and the number of events in the time?
Say again?
And first you sum over all the time, like from minus infinity to infinity. And then
Yeah, this is over all time.
this is all time, the number of events in all time, and if you
This is not the number. This is just the probability distribution of events. Okay? And so I integrate over this for all time, for the times of all events, from minus infinity to infinity, but for one of the events, I integrate only from TA to TB.
and what is the meaning of, like, if you do this?
What is the meaning of doing this?
Why do you don't count off from minus infinity to
For that event? Because I had the indicator here inside the integral. So the indicator takes the integral outside this time range to 0. So for one of the events, I can simplify and say that the integral is only on this range. Okay, so we leave this as it is for now, and we can also ask what is the average square of the number of events. Okay, and this is useful to ask because it will give us something that we can say about the variance in the number of events. So how do we compute this? Okay, this is the average, and inside the average, we have just the square of the sum that we had before. Okay, a sum over chi of tau sigma, and this sum is squared. So yeah, okay. No, wait. So now we have summing from S equals 1. The summation here starts from S equals 1 because S equals 0 means no events, and it will give us nothing for the average on the number of events. But in general, the summation should have started from 0. Okay? I move to the next row. This is multiplied by I write this explicitly so it'll be more clear. This is the first sum, and then we have the second sum, and we can say that the index is now sigma prime. if you think of what is written here, then this is okay. You have phi of tau 1 plus phi of tau 2, and so on, and it's multiplied by the same expression. So we'll get two different types of products. We'll get products that are phi of the same event squared. And we'll get mixed products. So here we'll have phi of tau sigma times phi of tau sigma prime okay, so we have S such components, and we have S times S minus 1 such components. So I'm going to break this expression into two. The first one will have the integral with this inside the integral. The second one has the integral and this inside the integral. So continuing this, I have, okay, n square average. This is from the first component. This should be sigma, right? No, S. This is from the first component. Now I have S minus 1 factorial, okay, because this gave S identical components. So in the numerator, I should have had S, but it's canceled out with the S from the S factorial, with the last component in the factorial. Okay, so now I have minus infinity to infinity, d tau 1, phi of tau 1 squared, and then all the rest, d tau 1, so d tau 2 to d tau s, qs of tau 1 up to tau s. This is the first component. Yeah?
Can't you construct a probability distribution function for your variable from capital N?
For
Let's assume
yeah.
a probability distribution function for N. Okay?
Mm-hmm.
That can calculate any non-trivial once you have the function, right?
Yeah.
Okay, so why can't we construct in some way this function instead of
So we're getting there. Okay. Okay, and this is from the second component. So s equals 1 to infinity. And now here I have s minus 2 factorial. Now, since phi can be either 0 or 1, this square here is redundant, actually. And the expression I have here from the first component is just the expression that we got last time for n average. Yeah, okay, and here I could replace this with TA to TB, right? Because we know chi is 0 outside of that. Okay. So basically I have the average n as the first component plus second component this is basically the same.
Why is the an average again? You have the C square?
Chi can be either 0 or 1. If it's 0, then the square is 0, and if it's 1, the square is 1.
Okay.
So I don't... Chi square is equal to chi.
Okay, but
Okay.
the
Yeah. So when chi is 1, then it means we have the integral. So we have an integral from minus ta to tb over d tau 1. Okay? Okay?
I understand this.
If chi is 0, then it gives us nothing. So you do the integral.
But here you don't have C, so.
Yeah, because doing
It's just translating.
okay,
Okay.
okay, and I can also write the square. So because of this expression is identical to that, and we remain with what I wrote.
But how do you know that
Minus?
this is 1? Because the integral is over this
No,
tau.
chi is defined as 0 everywhere, and 1 if what?
Okay.
Okay. Okay. So we got this, but this is defined as this, okay, with this function that I told you we don't know how to calculate right now. And just for our convenience right now, we define a sequence of functions Fn. This is basically, I think this is what Chagai offered just now. Okay, so this set of functions is just what we had in the expressions. We already saw the two first functions. Okay, it's not exactly, but it's almost. So the first function is identical to this one, except for this integral. I just define it. So now I don't have to write this again every time. Okay? The general formula, I'll talk later about what these functions mean.
You want to write T1 to TS, right?
What?
Fn T1 to TS, not to T2.
From here?
No, in the bottom row.
From, yeah, not to T2. Tn. Okay, so this is a general form. So what we had earlier, this average n can be written as an integral from Ta to Tb over f of T1 dt1, right? And what we had here, n squared can be written as n average and an integral over f2. It's a double integral, actually. dt1 dt2. So, yeah.
The right f of T1 to Tn, the T1 to Tn are not
Where? Here?
everywhere. Yeah.
T1 to Tn.
It's f of T1 to Tn.
Yes.
But T1 and Tn are not. Huh?
T1 and Tn are times.
No, they're not there. They're not in the expression at all.
Oh, yeah, you're right. Okay, I overlooked this. T1, tau 2. So here you would have T1, T2, tau 3.
So they are fixed.
Yeah, so these are kind of fixed values. Yeah. And here as well, so you would have T1 up to Tn, and then tau n plus 1, tau s. Right. So they are kind of fixed. So this thing, Fn of T1 up to Tn, is the probability that each small interval, where can I write it? I'll write it here. It's the probability that each small interval, T1 plus dt1, T2 plus dt2, up to Tn plus dtn, contains an event. Okay, it's basically the joint probability for events at these times. Okay, so the properties of these functions, f, first of all, they are non-negative, and they are symmetric in their arguments. This is based on our assumption from before that we don't care about the order of the events. We don't give them names and care in which order they appeared. We just care about their time. So, and these functions are in fact probabilities. They're not probability densities. See, here the probability density is inside the integral, and the function is already an integration over the probability density. So these functions are probabilities to have events, and when we integrate over these functions across a certain time range, we will get a number of events, or an average number of events. Okay, so F1.
What is the function that defines that it's beta 1, that event time?
Just a moment. F1 is the average density of dots, or point events, and higher Fn, we can call them average joint densities. Yeah, what was the question?
What is the function that defines the event for beta 1 from time to that?
I don't understand the question.
The function that, like everything is here from beta 2 and none of them is for
beta 1. Yeah, so it's because you integrate for each event you have a dimension. So you integrate over all the dimensions except the first one. Okay? But this probability density function contains also the first event. Okay, so how would I say this? So you integrate over everything, and you find, and finally you also do an integral over this one. Okay, only this has a limited range in time. Okay. So we'll go back to these functions and say some things about them, but for now we will consider a special case that will allow us to simplify the expressions that we got and actually get a real number of events and real distributions. Okay, so our special case is the one in which QS can be written as a product of functions, and each one is for a specific event. So what this means is that our events are independent. Okay, each event happens regardless of how long, how much time passed after the previous event. Okay, or the previous events, or how many events there were, or whether they were clustered or not. Everything is independent, and the probability of having no events is what I wrote here. This is e to the minus n. Okay. And this is used for normalization, and we have n is the integral over a single q tau. Okay, so now if we want to write the average number of dots or point events, this whole thing is divided by e to the power of an integral over q tau d tau. Okay, so I just substituted this for qs. This I wrote in the denominator. And here we have s times q of t multiplied by each other.
So, hold on. Everything is divided by, this means that it's...
This thing?
Yeah.
Normalize.
No,
Yeah,
so
it's a normalization.
Okay, so you said...
It's the normalization of qs. Okay, so I can write this again as I write this as e to the minus t for short. No, do I want to do this? No, let's do it. Okay, this shows you how we got this. Okay, originally this was an integral minus infinity to infinity over all the events, and okay. What I want you to notice is that here we have an infinite sum over this function to the power of s minus 1, that is the index of the sum, and divided by the power. So this is actually an exponent. It's the series expansion of the exponent.
What about with the integral between?
Which ones?
There are many integrals there.
These.
There are two integrals.
There is this integral.
Okay.
Okay, so this integral only depends
Power.
only on tau. So this
Okay.
could give you a number.
But
This is raised to a power and divided by this.
but the integral of d tau.
What?
The first.
The first one. Yeah, so
Not
no,
the sum.
disregard for now this integral. It's independent. I could take this here. Right? I don't have any tau here. This actually should have been let's say it's tau circumflex. Okay? It doesn't matter. This is an integral. So this is independent of this. I can take it out. I can put the sum just here, preceding this this integral raised to the power. This is just the series expansion of the exponent. This can divide everything because there is no index here, right? So the idea is that what I have written here is a series expansion for an exponent. If I replace s with s minus 1, so I start from 0 instead of 1, and here I have s, and here I have s. That's a series expansion of an exponent, and that will cancel out with the normalization factor. So this is just so this will be the average number of dots. And if we go back to what we had here for n squared averaged, we have n squared averaged if you do the same for this one, you'll still get the power expansion, only you will do the replacement nu s equals s minus 2. And here you will have two integrals that are the same. Okay, it's hard to see, but 2, this comes from TA, TB, dt1, qt1 times TA, TB, dt2, qt2. So you can write this thing.
What log is n or n?
Okay, this thing you can write as n squared. This is the square of this. So n squared is the n squared average is the square of the average n plus the average n.
Why is that?
What?
Why is that?
Because what we got when we developed this was first we got it was here. It was n average plus this thing, this long thing, that if we have a QS that can be factorized, okay, because of the independence of the events, we can do the same thing we did. Where is it? We can do the same thing we did here and end up with this only squared. Okay? So this is why this equality holds. And so when you rearrange, okay, so you got the n squared minus n squared, right? This thing equals n average. And this thing is just the sigma. Okay, this is just the variance. So when we had independent events, okay, we could write our probability density function as a product of individual probability density functions. We got this result. We got that the variance of the number of events equals the mean. Okay, and this is a distinguishing characteristic of the Poisson distribution. Poisson distribution is a distribution of point events that are independent of one another. Okay. Okay. You can also say that the Poisson process has a final factor, which is the variance over the mean of 1. okay, since I don't have enough time to do the whole derivation of the next thing, I will just write the beginning and the end result. So for independent events, when we write the characteristic function, okay, exponent of ikn averaged and instead of n, capital N here, instead of n, I can substitute the sum that we used before. And then you can write explicitly how the averaging gives you a sum over S and an integral over the probability density QS, and break down QS into the product that we showed before. And then when you rearrange, when you write things as exponents instead of a series expansion, you get finally that this equals e to the minus n sum over average n. Okay, sum is over n. And last week we saw that when the characteristic function is written as a sum over exponents, the prefactors are the probabilities for these numbers of events.
Every time in this sum you plug a number between 0 to infinity.
Yes.
So what's the meaning of the mean of it? What does it mean?
Just a moment. Okay. And this gives you the Poisson distribution. It tells you what is the probability to have a specific number of events in this process.
Why the symbol of mean goes
Of this one,
side of the
this thing. So, the way this mean is the mean number of events inside a certain interval, like we had TA to TB before.
But n is a random variable.
N is?
Here, according to what you wrote. N is running this
Yeah.
distribution, right?
I think you can do this without changing it. Okay. Yeah. So this thing gives you the probability that you have, say, 9 events within a time interval. Okay. So this would be the average number of events inside that interval, and you want to say you have a process that produces on average 20 events within 2 seconds, and you want to know what is the probability that right now in a specific instance it produced 9 instead of 20. Okay. And this is a Poisson distribution. Okay, to say some things about the f functions that we had earlier. Just we'll do this for 5 minutes and then we'll take a break. So these functions, you see they are derived from the Q functions, the probability density functions, but they are not normalized. Okay, and this is the difference between them and the probability density. And and the idea is that the meaning of this difference is that Q, the probability density has to vanish at infinity. Okay, because it's a probability density, it has to be normalized. So in order to normalize, you integrate from minus infinity to infinity, and you can't have things exploding at infinity. So Q has to vanish at infinity. The F functions do not have to vanish at infinity, and so they are more suitable for physical processes. Okay, they don't have this restriction. Okay, so a specific case that is more interesting for physical processes is the one in which the process does not vary with time. So Fn of t1 plus tau, t2 plus tau, and so on equals Fn of t1, t2, and so on. And this is called a stationary process. This means that it doesn't matter when you take your 2 seconds. Okay, you say you record from a neuron and you record at the beginning of your session and at the end. And if the firing of the neuron is a stationary process, it doesn't matter. You should get the same result. Say you have a process of point events which are occurrences of earthquakes. Okay, so or minor earthquakes. So a stationary process means that it doesn't matter on which day you record this process. And you'll get the same number or the same average number of events. So for a stationary process, you will have F1 constant. And if you combine stationarity with independence, which has QS as e to the minus ni times the product of the Q tau, then this is what we call shot noise. So the joint probabilities are powers of the average number of events. F1 is
the probabilities for one event in a time window, you chose?
Yeah.
What do you mean
So
it's constant?
what?
What do you mean it's constant? On what does it depend? When you have probabilities for one event and probabilities for two events, probabilities for three events, do they change?
it's a number. It's just a number. This f1. It's not. So it's not. It's no longer a function of time. Okay.
No matter what time window you choose, you have the same probability.
No, yeah, it doesn't. So f1 is a kind of density. So it's you. It matters. The length of the time window you choose matters because you integrate over f1 and you get an average number of events. But over the whole time scale, you have a constant probability of an event occurring. This is why it doesn't matter that you add this tau. Okay, you come back in a day or in an hour, and you'll get the same average number of events per say the seconds that you measured, or the 2 seconds that you measured. It depends. You need to compare the same time period at the different time points. Okay. And this will be so this will be a homogeneous Poisson process. Okay. So it's not only that the events are independent, you also have homogeneity across time. Okay, let's take a 10-minute break. Then I'll say some general things about stochastic processes, and I'll introduce Markov processes.
Naono, naono. Salom mרגיש שמגיע לך?
Okay. So last week I said some general things about stochastic variables, and since then we have been studying a type of stochastic process called point process, okay, or random events. And now I'm going to say some things in a more general sense about stochastic processes. So a stochastic process is a process that depends on both a stochastic variable and on time. Okay, so a stochastic variable. So the stochastic variable will be x. So it's some function of its variable n of time, and when we substitute a specific value that this capital S can get, we get what we call a sample function, or a realization of the process. Okay? So that would be written y with a lowercase x equals a function of lowercase x and t. And this will be a realization okay, say we are looking at the number. Yeah, okay, so the number of cars entering the city on a given day. And then this thing changes during the day, okay? So we have some function of time. It gives us a different rate of cars entering in the morning and in the afternoon and at night. But it also depends on other certain things. Say it depends on what month of the year it is. So we could say that we have in X, we have the month of the year. Maybe it also contains the weather, something about the temperature, or the amount of rainfall on that day. So when we substitute one thing, a certain value, we'll get a realization of the process. And the output that we get should be different for the different realizations. Okay, so the number of cars entering the city per day will be different for a hot day and for a cold day and for a rainy day and a non-rainy day, okay, and a snowy day.
And we don't take into consideration any connection between they shouldn't be either no תלויים בבדיחה. I mean,
Which ones? The time and the X?
say the day and the hotness of the day. What day it is in the week and
yeah, assume they are. Yeah.
they're independent.
Yeah, that was just an example. Okay. But yeah, in my example, you assume they are independent. Okay, so the general stochastic process can be regarded as an ensemble of these sample functions. Sample function.
What is sample function?
A sample function is one instance of the stochastic process that has a specific value for x, the stochastic variable. So if you average over all the values of the stochastic variable, you will get the stochastic process that is an ensemble of all these realizations. Okay? And it can give you, say, the average function of cars entering the city versus time of day. Okay, and for all types of weather. The probability for the variable capital X to get the value of small x. X is a stochastic variable. And you integrate over all the values it can get.
You can take also one realization. So instant time, it's going to be the same thing, right?
If it's an ergodic process. We'll get to that. Okay, so we have this stochastic process, this ensemble, and we can also use different values of times in order to compute moments of this process. Okay, so previously we had the moment as an average over a product of our stochastic variables, but here now our product will be composed of this stochastic process in different points in time.
What is this product?
This is a moment. The nth moment. Okay. So again, you average over all values of x. You integrate over all values of x weighted by their probabilities, and a product of what the process gives you, the output of this y, at different points in time. Okay, so you can see that this was actually a first moment. This is a general case, and a particularly interesting moment is this second moment. Okay, this is a notation that I mentioned, but I did not introduce explicitly. But it just breaks into this.
So
yeah.
Just to make sure that I
Yeah.
understand. So the average is for a given time, right?
The average is for a given point in time. Yeah.
A point in time though, or does it have a length?
No, it's for a given point in time here. Okay. So you could ask.
So it has a length.
What?
A small one.
Here.
I mean.
Well, no. No, but I want to know what is the number of cars. Okay.
So
yeah, I guess.
Do like a day, right? Like a day could be a time, like on a Sunday, right?
On a Sunday, or at 3 a.m. on a Sunday.
Yeah.
Okay.
And then T1, T2, the lower one, just different days or different times during the day.
Yeah. Mm-hmm. So this type of second moment, you remember that this is similar to the variance, okay? But it's not an actual variance. It's a more general case. This is this is the autocorrelation function. When you have T1 equals T2, this reduces to the variance. Okay, so this average could have a certain variance around it, right? And this would be a measure of the distribution of events around the average for a certain point in time. But when you take this, you would ask how much is the number of events that I am going to get here dependent on the number of events that I'm going to get here. Okay.
It should be also double brackets on the right side. Double brackets is overrealizations, right? So it actually should all be double brackets.
No, the double brackets here are the notation for a cumulant, and cumulant is kind of equivalent to a moment. It's a different. If we have moments that are different powers of y under brackets, the cumulants are something a bit different. But there are if the moments are a system of measures that describe our stochastic variable or process, the cumulants will be an alternative system of these measures. But yeah, so the second cumulant would be kind of taking the central moment. Okay, it's equivalent to taking the central moment, a product of them. Okay, yt2 but the third cumulant is on and on is already not equivalent to the. Okay, if I had taken just the second moment, then I wouldn't get the variance. Okay, the variance is the second central moment. You subtract the mean before you do the square.
So this is the definition of the double bracket?
No, I don't want to give the definition for the cumulant. This is for the second cumulant.
So what expression?
If there was yt1, yt2, yt3, then it would be different, right? You already need to write it differently. But this is, okay, I use this notation because I cannot write this as yt1, yt2 with a single bracket. It will not give me this. But this is the autocorrelation, and the degenerate case of it is the variance.
So what you wrote down down there is also equal?
Here? Yeah. Hmm?
They're both equal?
Yeah, they're both. Okay, so a lot of times we are interested in stationary stochastic processes. And this is similar to what we said before about the stationary point process. In a stationary stochastic process, the moments are not affected by a shift in time. This is getting unintelligible. Okay, so we saw before what a stationary point process means. This is a general case for a stationary stochastic process. For all n, tau, and t1 up to tn. So all the moments, not only the first and second, all the moments that you can write are invariant in time. Another definition that I want you to know is a zero mean process. So it's more convenient a lot of times to work with the zero mean process. And it's the same as what we saw with the stochastic variables. Okay, so y tilde is just y minus the average of y.
Average
Over what?
over time or?
No, the average over realizations. Okay. Okay, so for a stationary process, the autocorrelation depends only on the difference between the times.
Does not necessarily time itself.
Yes. So when I look for an autocorrelation, I would ask what is the correlation between the number of cars at 8 a.m. and 10 a.m. Okay, and so these are T1 and T2. So for a stationary process, it doesn't matter if I take this 2-hour difference and I shift it during the day. So I guess the number of cars entering the city would not be a stationary process across the day. But what you need to know about this is that indeed the autocorrelation function is something that gets a certain value for any 2 points in time, and in a stationary process, you replace this just with the time difference between the points that you're measuring. So often you would plot the autocorrelation okay, and of course at 0 it should be 1, and then it might decay in a certain way until there is no correlation. And often there is some constant that we mark tau c such that the autocorrelation is either 0 or approximately 0. Let's mark it like this. For times larger than this. And this is something very practical. A lot of times you would take, say, the membrane potential of a neuron, and you would like to see when do the autocorrelations decay to 0. This is a kind of memory length for the process. Okay.
So this is not a stationary process.
This one, no, it's not a stationary process. But if you are willing to talk only about shifts in time that are larger than the autocorrelation time, then you can consider it a stationary process.
Yeah, if you look from tau c.
Yeah,
There is
exactly.
transient, and then
Exactly. Okay. Yeah. Okay. This was exactly the next point I was going to tell you about. Okay. So sometimes y could have several components. So it will be actually y jt. So you could think of it as a multidimensional thing, an array of numbers. And then instead of kappa, you have an autocorrelation matrix. And illustrate, this autocorrelation matrix would have on its diagonal the autocorrelations, and here, well, all the non-diagonal elements will be cross correlations. Okay, so a lot of times, if you have an array of electrodes and you record from different sites or different neurons, you would like to know the cross correlations between them. If you have, and then you could maybe identify links. So if one neuron fires, then another neuron is characteristically fires half a second after that.
Cross correlation, you mean realizations of different x's?
No. A cross correlation would be when your process is multidimensional. Okay. So a cross correlation would be
x1 to xn?
yeah, from x1 to xn. You have I don't mean, sorry, I don't mean different stochastic variables. I don't mean the x. Maybe the x is one variable. Maybe it's several variables. But the y has different variables. Okay. The y is a vector, and you would like to know how one component of the vector depends on the other component across time.
Here, for all the metrics, is for T1 and T2. Will all
What?
all
Say
the
again?
metrics from T1 and T2.
The whole matrix?
Yeah.
Yeah, the whole matrix is for a certain T1 and T2. Yeah. And if it's stationary, then it's for a certain tau.
Okay.
Yeah.
So for the diagonal, it's supposed to be the higher correlation from all the
The diagonal?
yeah.
If you're asking if the diagonal is highest here?
Not necessarily.
I think not necessarily. So it's possible that okay, say one neuron number one forgets events after 1 second, but after 2 seconds these events in neuron one cause an event in neuron two. So neuron one fires for an event and it then wanders off, but when you take a tau of 2 seconds, you see that neuron 2 is very much dependent on what happened in neuron 1. It could in principle be that that one component, the I component, doesn't remember what happened to it 2 seconds ago, but the J component remembers what happened to I. Maybe it just stores it in memory. So, yeah.
The different dimensions of y must be with the same x, the same rational function.
No, they don't have to be.
Different parameter as well.
Yeah, they can be.
But usually, what you get in the stochastic, you mean that the y can be different neurons,
That
the
y,
dimensions of y.
yeah. So it can be different neurons or.
If they are very dependent on each other, you have a high cross correlation.
Yes. Okay, so for a zero average, let's do this. Zero average stationary process. So now you no longer care which t's you take, so you can just as well take 0 for one and tau for the next. So kappa ij tau is just this. Because it's 0 average, I don't need to write the cumulant here. Okay, the cumulant will be the same as the second moment. And also the kappa is symmetric. This should be true for any stationary process.
Can you repeat what you said? Why you don't differentiate the
The what?
cumulant?
The cumulant.
Yes.
No, that was just a notation. When I wrote the kappa originally, it was for a general process that doesn't necessarily have a 0 mean, a 0 average. So here you see there is subtraction of the average. Okay? Here and here. But if it's a 0 average process to begin with, then I don't need this notation, and I can just write the second moment. Okay.
Okay, and why?
Just a matter of notation.
Can you you change between 0 to tau, and that's not.
Yeah. So kappa was for T1 and T2.
Okay.
Okay. But if it's a stationary process, you don't care. You just
Stationary, not because
stationary.
It's
This is because it's stationary.
and that's stationary.
Yeah.
Okay.
Okay. Okay. I will say this briefly. When we want to characterize a stochastic process, say experimentally, we would like to try an average over many realizations. Here. Over many realizations of the process. So what we could do is take several instances, several physical systems maintaining this process and measure them. Okay, say I have different cells in a culture, or different molecules. Okay, so I would try to measure from as many as I can, and then try to characterize the stochastic process. Alternatively, I could take one physical system, and maybe I can measure it in different time points, and then I assume that the stochastic variable obtains its different possible values, okay, across this time scale. The equivalence of measuring over an ensemble of physical systems and measuring over time is not guaranteed, okay, and processes for which these two are equivalent are called ergodic processes. Can I repeat what, everything? An ergodic process is a process in which taking the average over different realizations is equivalent to taking the average over time. Okay.
So how
what?
the average over y or t equals to
I guess I would write it like this. So this is the average over the x's. Okay, like this. So this, which is actually this, okay, would be equal to an integral over time.
this is the expectation or
I don't like this t here.
Should be yi. No.
What? No, this is yx. So
No, the left hand.
this
Yeah.
yi. No, it doesn't have to be yi.
Any y, no?
Doesn't have to be. No. The idea is that it's many x's. Okay. And here you assume that for each time point, x assumes a different value, and eventually obeying the distribution, the probability distribution of x. it just means that you would want to do this for long times, longer than the autocorrelation time.